Okay, let's do a last example on geometric sequences. We're still within the geometric sequences. We left off where we're talking about homework, and we are now picking up there, doing our last example. And we're saying here, if x minus 6 and x plus 8, if these, oh sorry, made a mistake. If x minus 6 and x plus 8, if those form a geometric sequence, find x. Right. And the way with you all guys, I do give you slightly different answers. Sometimes what I gave as an example for the other, I give as a example to the other. So you can literally help each other very nicely. I'm thinking about Abu. I gave Abu a question like this as an example, as a homework, yet I gave what I gave you guys as an example. As a homework, I gave you guys as an example. So yeah, anyway, you have, so if you work each other, you shouldn't really struggle. You have this and this and this. So you can blindly just say, you know what, let's look at, this is a geometric. So if I say x divided by x minus 6, I'll get what I got there. And I can also say x plus 8 divided by x. Right. But now what you've calculated there is T2 divided by T1, and that T2 divided by T1, if this is a geometric, it must be equal to T3 divided by T2. And therefore, this can be x divided by x minus 6 is equal to x plus 8 divided by x. Then we can solve for x. You can sort of like cross multiply if you've heard of that. You see, you can multiply those ones and you can multiply those ones. So you would have something that looks like x squared is equal to x plus 8 times x minus 6. And then you would have x squared is equal to x squared minus 6x plus 8x. 8 times 6, what is that?
It is 48.
Thank you so much. So that would be x squared is equal to x squared. Then what we're going to have here is plus 2x minus 48. If I take this x squared to the other side, I would be getting rid of x squareds, and I would have something like this. The algebra needs to be hard, guys, here. It needs to be like proper. Then you would have 48 is equal to 2x. Then you just have to divide by 2, and your x would be what? 24. Okay, so I just wanted you to find x, so x would be 24. And that's it for the geometric series. I just want to get a sense if people have questions or anything, things that you guys would like or anything like that. Any questions? Okay. Doesn't seem like that.
Not really.
Am I getting it?
fairly easy.
Did I get a question, guys? Jamie, did you ask something?
Now, sir, I see that this part of the patterns and sequences were this was fairly easy to catch.
Oh, okay. Okay. That's good. That's good. That's good. Okay. Now we're going to hopefully another part that should be easy to catch. Here, I'll talk about the series. There's an intercom going on. I'll just mute my mic. Okay, there's an intercom going on, and yeah. Anyway, we're going to talk about a series. We're going to talk about a sum. We're going to talk about sigma. We're going to talk about, I don't know, maybe some special cases. I don't know. But let's jump into it and start talking about perhaps a series. Lindo, are you still following?
Yes, sir.
Okay, awesome. So let's talk about the series, right? So basically, we have a sequence. We have a sequence, which is what we've been dealing with. It's basically T1, T2, T3, and it sort of like goes on to some Tn. However, a series is a bit different. You know, basically by definition, a series is basically a sequence is basically is called a sequence is called a series when the terms are being added, right? So if we start talking about T1 plus T2 plus T3, you know, you start talking about a series. Why am I liking the semicolon thing? Yes, then that's a series, right? So we're going to talk about the series, sum, sigma, and some special cases for sigma. So let's talk about the sum now. That's it about the series so far. We're going to come back to it in other lessons. Sum, so basically a sum can be denoted as Sn, right? And it basically means that you are just adding things together, T1 plus T2 plus T3. However, you can have a couple of sums. You know, you can have a one where you know the last term, you know, it means that it has an end. We call it a finite series. You can get a sum which you do not know the end. We call it an infinite series, and to normally be given by S infinity times T2 times T3. And as you do not know the end, you'll just go forever there. It's called an infinite series, an infinite series, an infinite series. Okay. And then, I mean, I'll come back to this when I'm doing questions, but you can find Tn using the sum. And Tn using the sum is Sn minus 1. please take note of that, right? Take note of that. You know, if you don't take note of that, I'll give you a question and then you're going to not know how to do it, and I'll gladly bring you back here. So that's involved in finding a term using sum formula. We're going to engage with this sum formula in a different lesson. Just want to let you know also, guys, these are 2 lessons that are going on here. We've done geometric, it's a lesson on its own. Now we're doing this series sum sigma in some special cases. They are a lesson on their own. So I'm just trying to compile quite a number of lessons altogether. Okay, going out from the idea of series, we now go, or on the idea of sum, we now look at sigma notation. I don't know, this scare people off. I don't know why. Sort of like scare people off. Okay, sigma notation. Let's talk about sigma. Remember we said a sum is, you know, if you're summing, for instance, 10 things, you can write that also as with this, maybe let me just not say that now. First tell you that this guy over here means the sum. Means the sum of whatever what is inside, which we're going to look at how to read it and talk about it. So if you're talking about S10, we know that S is a sum. So, you know, we said Sn is a sum. Where there is n, you know, we can talk about S10. It means that you are summing 10 things. And that could be written as with the sigma. Remember, sigma is the sum. And it would have R is equal to 1. And it can have 10. And it can have something that looks like TR plus 1. Now, this guy over here, that guy is the starting position. If you were not listening for the duration of this class, this is the most part where you would need to listen. This is the starting position. This is the end position or the number of terms that are being added or summed. No, that's summed, that are being summed. I have a problem with my laptop charger, which is bad. Just give me a second, guys. I just want to sort something out. Okay, I don't have a different laptop charger here, which is a big problem. Okay, looks like I do. Okay. So does anyone want to guess what is that 2R plus 1? What does it stand for? So what is this guy over here? That guy is our general term. So let's look at what this basically means. If you have something like this, Tn sum, this basically means this is the starting position, right? So when you're summing something like that, this is where you're starting, this is where you're ending. So you're going to be saying 2 at position number 1, what's that? And then you add it to, then you add it to At position number 2, what is the value? At position number 3, what is the value? At position number 4, what is the value? At position number 5, and so on. At some point, you're going to be like, and then, you'll be at the last one, at position number 10, what's the value? And you're basically summing all that thing together. Now, I want to just bring your attention to something different, or to something quite very interesting rather. And that is, the starting value, is not always 1. Is not always 1. The starting value is not always 1. And it's always important to then think about what happens when the starting value is not 1. So just look at it and think about, I'm sorry guys, please think about it. What could be a problem when the starting value is not 1? Normally, when you're faced with a situation like this and you don't know how to think about that, create a situation where the situation that you're trying to investigate. So let's see what's going to happen here. So let's say we're still looking at S10, and it's still the sum of the general term 2R plus 1, still going to the n value 10. R is at 4 now. Maybe nicely, let's say R is at 5. So this is now going to be 2R starts at 5 plus 1. We have that plus 2R is at 6 now plus 1. And then we have that R is at 7 now plus 1. Plus then 2R is at 8 now plus 1. R is at 9 now plus 1.
So,
Yes.
could you say that R is bigger or equal to, no, R is bigger than 0?
R is basically the position. So
If it's not 1, not always 1.
oh, yes. So if it's not 1, yes, that's fine. So R is not going to be less than 1 at any point because R is the position, right? So R is the position. I'm not sure if I said that anywhere here. Remember, maybe this idea of R is not sweet, but R could be your N. If there was N here, R could have been your N, but we don't like to use N because we normally use N for there. So R could be your N. So yes, definitely. Okay, but I want you guys to look at some big implication of this. So now here, if you look at this here, you were adding 10 things, right? So if you look at what this was saying that number at the top there, it's the number of terms that are being added. So in this case, we're adding 10 tens, right? But But in the example that I'm doing now, I can still say that's the end position or the number of terms that are being added and all that. I can still say this is the starting position. And I can say that my TN. But now, this applies more. This is just the end position. This is definitely not the number of stuff that are being added, right? Now, to give you an example, here is that you can calculate how many things are being added. 1, 2, 3, 4, 5, 6. There are 6 things that are being added. Now, there are 6 terms that are being added. And that's definitely, we definitely don't have 10. Whereas in that situation, we actually had 10 just by changing R, right? So think about it this way. If you have your pattern here, let's say it's 2, just choose a different color. Say it's 2, 4, 6, 8, 10, 12, 14. I don't know, maybe say 0 there. And this is position number 1. This is position number 2. This is position number 3. This is position number 4. Position number 5. Position number 6. Position number 7. Position number 8. So now, if your R, your starting value is at position number 1, this is where you're starting, sorry. This is where you are starting. The number of the items, so you're starting there and you're adding all the way there. So the number of things, number 1, your end position is 8. Let me just write it, end position. Your end position is equal to 8. And the number of terms that you are adding is also 8. But if you somehow change your position, your starting position to be like 4, the number of things that you are adding, so maybe to start off with, your end position of the series that you are still using is still 8. But the number of items that you're adding are definitely not 8. You're starting at 6, you're adding 6, 8, 10, 12, 14. So you're adding about 14 things. You're adding 14 terms. Sorry, 1, 2, 3, 4, 5. You're adding 5 terms, my apologies. You're adding 5 terms. You're adding 5 terms. So you can see literally by changing R, you can start elsewhere. And therefore, if someone gives you S10 and say, this is the sum of 10 things, R is equal to 1, and this is 2R plus 1, and then give you another one and say S10 is equal to 10, sum of R is equal to 3, the same, or give you another one where they say S10 is equal to the sum of 10, R is 0, and you are with 2R plus 1. 2R plus 1. And for this sequence, you just think about how many stuff you are adding, how many terms you are adding. So you can see in the first case, you're starting at 1, so the number of things that you got adding are just 10. Remember I referred to this 10 as n earlier on, so I'll just say new is equal to, the new n is equal to n. Whereas here, you can see that you're starting at 3 and you're going up to 10 terms, so the number of terms that you are adding is going to be different. So the way we calculate it is that we say n minus r plus 1, right? So in this case, n new would be equal to 10. If you want, actually, let me just do it this way. r plus 1. So if you want, this is going to be 10 minus 1 plus 1, which is equal to 10. And then here, we're going to have a situation where we have 10 minus 3 plus 1. So here we're going to be adding 8 things. You know, we're going to be adding 8 things. And there, if you want to say new, is you're going to be like n minus r plus 1. Your n is 10, your r is 0. So here you're going to be adding 11 things, 11 terms. And, you know, you see how these are. So that's how, so I just suggest that every time when you're dealing with the sum and you need to find n, the number of stuff that you are adding, just always say n new is equal to n minus r plus 1. But what is n? N is always that term at the top. Oh, I didn't give it to you guys like that. That's why it's weird. That's why so n would be what is normally there. Then r is equal to 1, and then 2r plus 1. So n is basically this term here. Whatever that number that is there, it's normally n. So again, if there is any point where you were not listening, this is one of the important things to recall. But now, that's me just talking about sigma. Let's look at how does one write sigma, right? So let's look at writing in sigma notation. So step one has to write down like just the sigma, and always just start at 1 if you're creating your own sigma notation. Step 2, find the general term. Find the general term. And note that your general term must be in terms of r. So you can't just come with the general term that's 2n plus 1 while you're saying r is equal to 1. Because when someone wants to know what's the first term, they're going to want to substitute r in your general term. And therefore, if you have a different variable there, they will think that 2n plus 1 is a constant kind of thing. And what r is not influenced. So you will rather write this as the sum of r is equal to 1 to r plus 1. So this one is incorrect. And step 3 is basically find the end value, right? And how do you find the end value? That's what we did earlier, where you say Tn is equal to your last term. Do you guys remember that? Take you back just to recall that. This is what we were doing here when we were finding the last term, you know, the end position, right? So we just took that term, we set Tn equal to the last term, and we solved for n. And that's your last step in trying to write things in sigma notation over there. And yeah, I have a few special cases. I'm actually just not going to tell you the obvious one. I'll tell you the not so obvious one. If you're summing n things and you're starting at I is equal to 1, do you see here, when I change my index to be I, my term is in terms of I as well. So that, I can substitute to it to get my pattern like that. If I do this up to n terms, and n terms suggested by that guy over there, then the way that I can write this is I can write it as n plus 1 divided by 2. That's a special case. So in that special case, you must always start at 1. Now, there are a lot of problems that I can give you guys to look at here. They could have been examples. I don't really have time to actually do them. The first one, is basically use the general term tk is equal to 5k minus 2 to determine S6. The second one is if Sn is equal to 3n minus 1, determine T5. And then the third one is just to get a sense of you understand, what's going on here. Expand this sigma notation. Just expand it. When I say expand it, I mean just say, like for instance, this one would be just 3. Sorry, it would be 1 to the power 3, 2 to the power 3, 4 to the power 3, 4 to the power 3, and 5 to the power 3. Done. You've just expanded it. So I've kind of done number 1 for you, just for you to get a sense of what's happening. And then you can expand that. And then you can then evaluate. For evaluating, remember, sum is a sum. So for evaluating, I actually want the sum. What is the actual value of the sum that you are giving me? What is that equal to? This is really not difficult, guys. Really not. Just don't want to drag this class to be longer than this. It's really not equal. It's really not difficult. And then what number was that? Number 4, number 5. Number 5 is express the following in sigma. Now, guys, I want you to note that this is not a homework. This is the homework that was supposed to be examples. So you can give it a try, but chances are if I meet you guys again, I'll go over this as like examples. But it's nice just to see them and see what is expected of you in this chapter. So the last one says, write that in sigma notation. And yeah, that's it from me. Do people have any form of questions? Jamie, can you please help me? Go to OneNote, take a link for the notes, put it on the group so that Lindo can get it. Guys, I couldn't even introduce you. Guys, we do have a
So
new speaker.
I don't. My OneNote does not work.
Oh, really? Can Shana do that for me?
So Lisa Kanya also tried helping me, so mine also doesn't seem to want to sync with people's.
Oh, that's interesting. Okay,
So
I've
Lisa
done that.
Kanya is usually the one that sends it to us.
Oh, okay. I will do it. I will send the link just now. Um, I didn't even manage to introduce you guys, and it's almost end of the class. Hopefully, I'll manage to do that next time. Tomorrow, I hope everyone could be there because part of the session, people would be representing or presenting their solutions to the TAT. So scan your TAT, have it ready on your laptop, or if there is one of you that doesn't have a laptop, send it to me earlier. Oh, sorry, I have it. I will basically say, go to your solutions, please present number 4. And then I'll ask Jamie to present number 4. I'll ask Shana to present number 16. And then I give you marks based on your presentation. Shouldn't,
So which task is this?
oh, assignment.
Oh,
Yes, that's the assignment. And that's how it's gonna go. Please tell everyone that's how it's gonna go. And that's basically it from me. Everyone happy?
yes, sir.
Okay. Guys, sleep well. I know you guys are gonna sleep at 4 tomorrow morning because you're gonna be working so hard.
Sleep well, sir.
Thank you. Bye. Bye, guys. Good night,
Bye.
everyone.
Thank you, sir. Bye.
Good night, everyone. Short cheers.
Good
Good
night.
night. Bye.